All right, so today we're going to work on the 5.8 notes, which is modeling scatter plots to best fit a set of data to a function. So we're going to use our graphing calculator here to do this. So with each one of these, what we're going to do is we're just going to take our data, we're going to plug it into the stat button of our graphing calculator, and then we're going to run three different regressions, a linear, a quadratic, and a cubic regression. And then see which one fits the data the best. And the way that we'll figure this out is by using our R value. So again, if to make sure that you are able to see the diagnostic on a calculator that's newer, you can go down to Stat Diagnostics. So if you hit the Mode button and go down to Stat Diagnostics and make sure that they're on. If you have an older calculator, you can go to the catalog and you can scroll all the way to boom, where it says diagnostic on. So you click the second button and then the 0, which will take you to your catalog, and then scroll all the way down to where the D's are and diagnostic, turn diagnostic on and hit enter. This will allow you to have your R value that shows up on your calculator when you do your regression. So first thing we're going to do is go ahead and get in here. Again, you're going to clear your tables out. Make sure you don't delete, make sure you clear. And then once you're here, what we're going to do is we're going to plug in the data. So our X values of 0, 5, 10, 15, and 20 will be in our L1 column. And then in our Y will be 10.1, 2.8, 8.1, 16, and then 17.8. So again, to get there, I hit the stat button, I hit enter. That's how you get to edit your lists. And then once we're here, we're going to hit the stat button again, and we're going to go to the right. And then three different regressions we're going to do are a linear, a quadratic, and a cubic regression. So here, we're going to do first the linear regression, go all the way down and hit calculate. And so again, it gives us an A and a B value. So when we write our equation, we'll write it as y is equal to 0.57x plus 5.24. And then we know the correlation coefficient for a linear function is going to be our regular R value, which is 0.74. Once we get that, then what we're going to do is we're going to go ahead and go back and do a quadratic regression. So hit the stat button, go to the right, go down to where it says quad reg, the fifth option, hit enter, and then calculate. And again, this is giving us again another regression. So my A value is the coefficient for my x squared. So our equation will be y is equal to 0.06x squared minus 0.62x, and then plus 8.21. Our correlation coefficient in this case is our R squared value, which would be 0.76. And then the last thing that we'll do is we'll go back to hit the stat button, go to the right, and then go down to where it says cubic regression. Here, and again, I'm getting a really close R value. So this would be, again, my A is my coefficient for my x to the third, B coefficient for the x squared, C coefficient for the x, and then D would be our constant term there. So my equation would be y is equal to negative 0.01 x to the third plus 0.43 x squared minus 3.30x plus 10.08. And then that correlation coefficient right there, if we round to the nearest hundredth, it would end up like rounding up to 1.0. I'm going to put it down as a 0.99 just because it isn't exactly 1. And then when I compare all three of my correlation coefficients, I want to find the correlation coefficient closest to 1. So I would say the function model that fits the data best would be the cubic function, because it has the closest R value to 1, being a perfect fit. Down below, the next question, just going to take those ordered pairs. So again, I hit the stat button, I hit enter, I clear out my lists, So my L1 and my L2 column. And then I'm going to plug in my x values are 0, 1, 2, and -1. Whoops. I forgot I got to click. Can't do a subtraction sign on my keyboard. Be a -1. And then my y values will be -3, -1, and then 5, and -7. And then I'm going to go ahead and do the same thing. Once my data is plugged in, I hit Stat, I go to the right, and I do a linear regression. So here, again, I get my A, B, and then I'm looking at my regular R value. That R value is really, really close to 1. So it's y is equal to 3.8x minus 3.4. And then my R value would end up being 0.98. Once I've done my linear regression, I hit the Stat button, I go to the right, I go down to my quadratic regression. Once I'm there, so it gives me, I've got a R value of 0.976, and so this would be 0.5x squared plus 3.3x minus 3.9. And I'm going to write down that correlation coefficient as 0.976. It would round up to 0.98 if I was rounding to the nearest hundredth, but just because the linear regression was 0.98, I'm going to go ahead and leave it as 0.976 to make sure that I know that the linear regression right now has a closer to 1 correlation coefficient. And then the last thing, do a cubic regression. So hit the Stat button, go to the right, and go to a cubic regression. And this one is a perfect R value. It's a perfect correlation coefficient. So it would be, I could write it as x to the third minus x squared plus 2x minus 3 with a correlation coefficient of 1. And again, I would know that the function model above that fits the data best is the cubic because it has the closest R value to 1. We'll flip over to the back side of the notes. Again, same thing here. These are all the same. So as I go through here, there we go. So my x values are -2, 0, 2, oops, that was a 2, and then 3. And then my y value is 1, 5, 9, and 36. So when I do this, again, I can hit Stat, go to the right, go to linear regression, go all the way down to calculate. Should have this equation as y is equal to 5.81x plus 8.39 with a correlation coefficient of 0.81. Once I've done that, then I go back and do my quadratic regression. And there, got a R value of 0.87. My equation is y is equal to 2.39x squared plus 3.51x minus 0.03. And again, with that R value of 0.87. And then the last one, doing my cubic regression. So here, I end up with 1.67 x to the third. And then this one's kind of curious because it's got this 1.3 e to the -12th. So this is scientific notation for 1.3 times 10 to the -12th. So to write my b value, I would write 11 zeros and then a 1.3. That is such a very small number that I will keep that as a 0 x squared and then write my c value there. So my equation is going to be 1.67 x to the third plus, then I'm not going to have a b value, not going to have an x squared because that's going to be a 0. And then my c value would be -4.67 x plus 5. And that correlation coefficient ends up being a 1. And so it's a perfect fit. So it would be a cubic, which would be fits the data best because the closest R value to 1, or correlation coefficient to 1. Then when I do that last one, whoopsie daisy, there we go. So when I do this last one, so again, with the scatter plot that I have of cheese consumption, really weird problem, we're going to make sure that we're not going to enter in 1910 as our X value. We're going to count that as our year 0. So then 1940, if 1910 is 0, then that would be 30 years after. And then it would be 60 years after for 1970, 65 years for 1975, 1995 would be 85 years, and then 2001 would end up being 91 years. Then here I go from 4, 5, 8, 10, 25, and 30. So when I do one like this, again, I take my stat button, go to my linear regression. So my linear equation with an R value of 0.84 is 0.27x minus 1.22, the correlation coefficient of 0.84. Go back and do my quadratic regression. My quadratic regression gives me an R value of 0.97, which would be 0.01x squared minus 0.29x plus 5.10, the correlation coefficient of 0.97. And then go back and do our last one, which is a cubic regression. And here, again, I still got this scientific notation, this e negative 5, so times 10 to the negative 5th power. And so that one, I can maybe justify getting this one here, because that would be 0.00, so it'd be 4 zeros after the decimal point, so 0.00009 x to the third minus 0.01 x squared plus 0.15x plus 4.04, and that has an R value of 0.9. And again, if I rounded that to the nearest hundredth, that would technically round up to 1. So I could round that to 0.998. I'm going to leave it as 0.99 just because I don't want us to think that it's actually a perfect fit, but it is really, really close. That would be the way that it would model the best. And then the last question, it says, use your chosen model to predict the amount of cheese consumed in the year 2023. And so what I would do is I would use this, so 0.00009. I'd plug in that x value. So I plug in, so 2023 would be 113. And then, let's see, minus, whoopsie, whoa, no. Sorry, overreaction there. Minus 0.01. And then again, that same x value, 113. Oh man, I almost forgot to cube that to the third power. This 0. That's squared after that. And then I've got plus 0.15. Oh gosh, man. I'm sorry, I'm all over the place here. It's hard typing this on that's a minus sign there in our calculation. 0.15 times, and again, I'm plugging in that year, 113, and then plus 4.04. So again, all I did was I took that cubic function, the equation that we got from our line of best fit, and I just plugged 113s in for every single x. So each of those 113s replaced the x of that equation. And then I can hit enter and see that in the year 2023, the amount of cheese consumed would end up being 23.16 pounds of cheese. So just in case you wondered, last year, what was predicted to be pounds of cheese consumed, that's it. So Hopefully that all made sense. Again, just using your calculator, typing in, using our stat button and edit. We're typing in our data and then doing 3 different regressions, seeing which one has the correlation coefficient closest to 1. And then that question that we did right there would be one where we are then plugging in a value to predict in the year 2023, because these notes were made a while ago, how much cheese would be consumed. So hope that helps.